So hi everybody, welcome to our project meeting in the third year. So today we'll have a number of speakers and I'm the first one. So first I will give a very brief overview of the project, but I'll focus mainly on my own contribution to the project that is mainly about coarticulation. First, just a very brief overview of the project. The project is called High Quality Simulation of Early Vocal Learning, and this is funded by the Leverhulme Trust. And the motivation of the project is that we know that adult speech comes from childhood vocal learning, because we all go through that stage. Without understanding the learning process, knowledge of human speech is limited. An effective way to understand the learning process is to simulate it computationally. In fact, in our view, without such simulation, knowledge of speech is inadequate. So our project aim is to significantly improve knowledge of human speech by computational simulation of vocal learning. So just a little paraphrase of what the title of the project means. By high quality, we mean using natural speech as the benchmark. And this is in contrast to some of the common practices of using an arbitrarily set low-level benchmark. And instead, we use natural speech as our benchmark. And simulation means to digitally emulate the learning process to the point of being able to synthesize intelligible speech. So we want to simulate the process to the end. Early vocal learning means to learn articulatory parameters from speech signals without adult speaker provision or explicit speaker normalization, and also without information about the, especially the hidden articulators. And here's our project team. I think, so we have members from Germany, Peter and Paul, from Macedonia, Branko, and also from University of Cambridge, and also from Thailand, Sanitam Proma, and the last three are all at UCL, Daniel, Anchi, and me. It's worthwhile to introduce the history of the project. So to a certain extent, the project doesn't start from scratch. We didn't start from ground zero. In fact, at the point we started the project, in fact, what is motivated by the project is that we were already able to use vocal tract lab with female and child vocal tract configurations to generate natural sounding vowels and glide vowel syllables with articulatory parameters learned from a female utterance. So in this respect, we have achieved some kind of speaker normalization without explicitly doing that. And the simulation is based on errors from comparison of MFCC parameters. And this starting point itself is already based on some of the knowledge that we had before. There are three major ones. The first one is the quality of the vocal tract lab. It is very high. It's a state-of-the-art articulatory synthesizer. And secondly, it's the target approximation model that is already implemented in the vocal tract lab for both laryngeal movement and supralaryngeal movements. And the third one is that in our simulation, before the project, we're already doing analysis by synthesis based on continuous MFCC trajectories of real utterances. And the aim of this project, first and foremost, is to be able to synthesize CV syllables where the C is not a glide. So because we were already able to synthesize a CV syllable with glide as the onset, as you will see soon. And the second goal is to be able to simulate corrective learning. And third one is to learn the effect of visual feedback. And fourth one is to see if we can use auditory templates to do the learning. And finally, we want to find out the potential role of babbling. And as you will see, not all of them are achieved. Okay, so for the starting point, I would like to show, for those of you who don't recall, or if there's any external audience, this is what we had before. So in this case, we use an original speech utterance.
Are you well?
And this is my rendition of the 5 Japanese vowels in a sequence. And this is what we were able to learn from directly mimicking this utterance.
Are you well?
And this is generated by the articulatory movements learned through the acoustics rather than through any information directly with articulatory parameters. All the articulatory parameters are learned from the acoustics. And we were also able to learn this particular German utterance with a male vocal tract and male vocal tract and 2 child vocal tracts.
Yeah, 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 yeah.
Yeah, 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 yeah.
This is the male vocal tract.
Yeah, 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 yeah.
It's 1 child vocal tract.
Yeah, 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 yeah.
Another one that is even younger. So if we jump to the next one, and here's what we have achieved so far. At least to me, the biggest surprise in our finding is that this is something, in fact, we didn't anticipate. It turns out, as we discovered through many trials and error, that speech perception actually provides a better guide for vocal learning than acoustic matching. And here, speech perception is simulated by an automatic speech recognizer. And acoustic matching is what we used to have, that is use MFCC fitting as the training data. One thing that is, I would say, is partially confirmed, that is, it seems that coarticulation dynamics based on CV syllables seems to provide a critical articulatory frame for vocal learning. This is something I will present next. But by partially confirmed, I mean we didn't test the alternative. That is, we basically tested our understanding. We didn't test whether alternative that is without synchronization, for example, would also work. So we don't know that. So that's why I say it's partially confirmed. And we did confirm the potential contribution of somatosensory and visual feedback. And they both seem to be beneficial for learning. So the significance of these findings is that the long-standing speaker normalization problem in this project seems to be largely resolved. We don't need to worry about speaker normalization as has been long held. But there is one thing that we did try, but we didn't achieve. That is, we were not able to find a way to simulate corrective learning. By corrective learning, it is that you learn from the mistake directly by correcting it in the opposite direction. And we could not fit into our learning algorithm. So either we can consider as evidence that it's not the main learning mechanism, or we didn't find the right way to do it. So the main component of my presentation will be focused on coarticulation, which I consider as syllable-based articulatory dynamics and coordination. So starting from the starting point of our project, that is, when we tried before the project to synthesize a CV syllable where the C is an obstruent consonant, were not able to do that. So this led us to think, what is so tricky about CV syllables? We can see that when we produce a CV syllable, we first close our airway to produce the consonant, and then open the oral cavity for the vowel. So in other words, we do the C first and then the vowel second. So the natural assumption is that because the closing and open happen in sequence, consonant vowel articulation must be sequential. But a puzzle that is long known is that we also know that neighboring sounds affect each other extensively. So for example, if you start from the conventional segmentation of segments and syllables as presented as in a tutorial by Turk and others in 2006, you can see this is our current understanding of how the segments should be separated from each other. Each time, it's the landmark, spectrographic landmark, that is treated as boundaries of syllables as well as segments. But at the same time, we also know that between them, there's a lot of influence upon each other. And this is considered to be coarticulation. So the accepted solution so far is that we simply call it coarticulation. And based on, according to Corner and Nolan, their definition of coarticulation is that very broadly, it refers to the fact that a phonological segment is not realized identically in all environments, but often apparently varies to become more like an adjacent or nearby segment. But critical question about the coarticulation remain. There are actually three major ones. First, where exactly does coarticulation happen? And second, why does it happen? And third, how exactly does it work? So first, the where problem. We start with the classical study of Ullmann, 1966. What he discovered in that study is that if you look at a VCV sequence in Swedish, like ögu, what you can observe is that the first vowel before the CV syllable after that, at the end of it, the second formant seems to point to the vowel of the next syllable. And so here you can see F1 is pointing to a closed consonant, and this is well known. But F2 is pointing to the next vowel. And this can be seen clearly in the fact that if the following vowel has a low F2, F2 in the first syllable is pointing down. So in other words, we can see the influence of the second vowel on the first vowel. And this is considered to be long distance vowel-to-vowel coarticulation. A clue that we can have to understand this phenomenon is from tone. So from my study of tone, what we discovered from tone studies is that in these three plots, the major difference across the three plots is the tone of the third syllable. So here we have high tone, here we have rising tone, here we have falling tone, and each of them is preceded by 4 different tones that are plotted in the same plot. What we can see is that the articulation process of each tone is such that all of them start from the end point of the previous tone, but then they all move to a common target. And this common target, high, rising, and falling, happen to be consistent with what we know phonologically these tones should be like. So high tone is high level, rising tones rising, and falling tones falling. So from this, what we learned is that the tone production happens inside the syllable. So inside where it belongs to. And also the way it is produced is to approach its underlying target. So if we apply this principle to our understanding of production, speech production in general, we come up with the target approximation model. So in this model, for every phonetic component, phonetic segment or tone, we have an ideal target, which is phonologically specified, but in the production process, this target is approached within the time domain that is assigned to this element. If we apply to that principle, and here I'm using a particular example that we use in a study. So in this sequence, if I produce it, play it, this is Mandarin sequence.
比尼鲁友善，
So the key is the first two syllables. The vowel of the first syllable is E, and the vowel of the second syllable is U. In the mirror image is,
比卢里伪善，
so here you have U followed by E. So the traditional understanding is that this is where the second vowel should be. It starts from the end of the consonant interval, and it ends when the vowel moves away from its position. But what we can observe from this is that the approximation movement toward this low F2 target, and in this case toward this high F2 target, actually starts from the middle of the preceding syllable. And if we treat this as the same as tone, we should consider this interval to be the interval of the vowel itself. And if we do that, the domain of the vowel should be shifted earlier by a significant amount. So now that we see where the domain of the vowel should be, we can also look at where the consonant should be. And the information comes from another study. Same study that we published in 2018. That is, in this study, we figure out a way to determine the onset of the vowel and the onset of the consonant. We call it a minimal triplet paradigm. In this paradigm, we have one contrastive pair that allows us to see the start of the divergent point or divergent movements toward contrastive vowel. So in this case, F2 starts to go down toward the U target, and this F2 stays high for the E target. So the divergent point between the two is treated as indicator of the onset of the vowel. But we have another very similar minimal pair that allows us to see the divergence between E and L. So this is E and this is L. And in that way, we can see an indicator of the onset of the consonant. So what we discovered in that study is that when you compare the starting point of the vowel and the consonant, they largely start at the same time. So we consider this to be the first ever clear evidence that consonant and vowel start from the same time. And after that, we did another study, which was published this year, in which we looked at the articulatory data as well as acoustic data. And both of them show confirmation of the earlier studies. So here's the articulatory data. What we can see from here is that the lip movement, you can see the divergence point for the rounded vowel versus the unrounded vowel. They start to diverge roughly at this point. And then we use the tongue tip movement as an indicator of the consonant movement. So the divergence between L and E seems to start from here, and this is for E, and this is for L. And when we compare the relative timing of the 2 points, basically we find no difference between the two. So this is an indicator that both of them start at the same time. So if we use this knowledge to take another look back at Ullmann's study, what we can realize is that this is actually an indicator that his data already contained our current understanding, that you can see the movement toward the consonant start from here and ends here, and then this movement toward the vowel starts from roughly the same point, but it ends later. So consonant and vowel start at the same time, although consonant ends slightly earlier. And CV coarticulation happens within the syllable. That is, if you treat this as the domain of the syllable. So the next question is, why do we see this kind of synchrony? Our understanding is that it's related to the famous problem proposed by Nikolai Bernstein. And he was tasked to figure out how to improve the efficiency of labor, manual labor. But in this research, he proposed that the most critical problem for motor control is there are too many degrees of freedom. So here's an illustration using Peter's vocal tract lab, and these are just a small subset of the articulators. And in order to produce any simple syllable, you need to control simultaneously so many movements, and there's many degrees of freedom. Bernstein's resolution was to imagine that there is a synergy algorithm, synergy mechanism, so that a synergy as a structure allows many muscles to work together. But the problem is the notion of synergy is kind of vague, because the vagueness that led to the one solution proposed by people at Haskins Laboratory. So here's one in Saltzman and others in 2008. What they propose is that you control the relative timing of different articulators through coupled coordination. But if this is the case, then we would see an increase of degrees of freedom rather than a reduction of degrees of freedom. So our proposal is to instead assume that one effective strategy is to synchronize all the related movements, because synchronization would remove most of the temporal degrees of freedom, so that in each motor movement, all involved body parts start to move at the same time, and there's no need to learn their relative timing. And this is for motor movement in general. For speech in particular, synchronization is done through the syllable. So in other words, the syllable is the structure within which synchronization is achieved. And this is the synchronization of the laryngeal, consonantal, and vocalic gestures that correspond to tone, consonants, and vowels. So finally, is the how. And this actually is not trivial, because both consonant and vowel involve supralaryngeal articulators. Sometimes they involve conflicted demands on the same articulator. So the question is, when that happens, how do you achieve so-called synchrony for the sake of the syllable? Our proposal is to imagine a mechanism that does dimension-specific sequential target approximation. Specifically, synchronization is achieved whenever consonant, vowel, and tone are not in direct conflict with each other. So in the cases of ma, ba, bi, because they're not in direct conflict with each other, basically you can do the tonal movement, consonantal movement, and vocalic movement at the same time. But when there is a conflict, targets are sequentially approached, so that the C movement consonant movement will happen first, and then the vowel movement will start after that. So critically, articulatory conflict between consonant and vowel can be managed at the level of the articulatory dimensions. So here's the example would be, in particular, velar stops. And here we can see that the vowel movement, as indicated by the lips, starts from this point. This is where the divergence between U and E starts. But for the tongue tip movement, what we can see is that between E and U, there is no separation of the tongue tip movement until this point, much later. And the interval here is actually where the L target is approached. So in other words, the first part of the tongue tip movement is controlled by the consonant because the consonant needs to complete its goal. The divergence toward the two different vowels has to start after the consonant movement is over. So here we see a particular case of articulator-specific sequential target approximation. In later presentation by Anqi, and she will show that you can achieve that with a single, for a specific articulator where the two different dimensions can be controlled by a consonant and a vowel in sequence. Right. So basically we have answers for the three critical questions about coarticulation. It happens inside the syllable, and the reason for that is to achieve synchronization of consonant, vowel, and tone, and for the sake of reducing degrees of freedom. And this is done specifically through dimension-specific sequential target approximation. So here's a summary of my presentation. The implication of my understanding of coarticulation is that syllable seems to be the basic unit of vocal learning. Specifically, coarticulation happens inside the syllable, and syllables are therefore relatively independent of each other. And this means that children probably learn syllable-specific consonant vowels rather than context-free consonant and vowels. So in other words, they don't learn segments, but they learn segments that are specific to specific syllables. So for each CV syllable, children need to learn which articulatory dimension are successively controlled by a consonant vowel, while others are entirely controlled by vowel from the syllable onset. And these strategies, in my understanding, have contributed to the success of the learning of high intelligible words in our project. And this is the end of my presentation because I've used up all my time.